Hello, my name is Bine Brank and I am a PhD student at Juelich Supercomputing Center. In this video, I will present some of the analysis on compiler auto-vectorization when targeting ARM Scalable Vector Extension. Scalable Vector Extension, or SVE, is a new vector extension for the A64 instruction set of the ARMv8 architecture. Unlike other SIMD extensions, size of the SVE register is not fixed, but rather constrained to a range of possible values, ranging from 128 to 2048 bits. It is up to a CPU vendor to choose the right SVE size that will better suit intended workloads. Since size of the SVE register is not predefined in the instruction set architecture, same binary can run on CPUs with different SVE lengths. We call such code vector length agnostic code. When porting applications to the new SIMD architectures, there are many different strategies on how to do so. If the application kernels are very performance critical, the developer might use inline assembly or intrinsic functions. This gives very high control over the code, but also requires more effort. If one aims for high portability and less effort, it might be a good idea to use SIMD explicit libraries or simply rely on compiler auto-vectorization, which is the main topic of this video. All major compilers, such as GCC, Clang, or ARM compiler for Linux nowadays support SVE auto-vectorization. In order to evaluate how good are compilers when vectorizing code, we selected two benchmark suits. First benchmark is ETSVC, an extended test suite for vectorizing compilers. First written in 1988, this benchmark was written for the purpose of analyzing compiler auto-vectorization. The new extended version features 151 synthetic loops written in C programming language. Loops are designed to test different categories of compilers' code analysis. This includes dependence analysis, vectorization, idiom recognition, reduction, recurrences, and many others. The loops operate on 1- and 2-dimensional 16-byte aligned global arrays. For our tests, array size for 1 dimension was set to 8192, and the size for 2D arrays at 128. The second benchmark suite is called PolyBenchC, a collection of programs with static control flow. This benchmark features 30 computational kernels taken from various application domains such as linear algebra, image processing, stencil applications, data mining, and others. In addition to the default configuration, we have also tested a version where keyword restrict is used with arrays when calling the kernel. This keyword signals to the compiler that no aliasing occurs, and as a result, compiler can perform more aggressive optimizations. In this context, we evaluated three compilers: GCC, ARM compiler for Linux, and Clang. We used versions GCC 10.2, ARM compiler version 20.3, and Clang version 11.0. In Table 1, you can see the compiler options for different compilers used. For all three compilers, we targeted ARMv8 plus SVE architecture. Furthermore, we enabled level 3 optimization as well as fast math option to enable fastest but not necessarily safest floating point arithmetics. In addition, we enabled induction variable optimization for trees on GCC and explicit enabling of floating point expression contraction for Clang and ARM Linux compiler. Successful vectorization was checked through the optimization reports, as well as through manual inspection of generated assembly. With each compiler, we have also compiled a binary when vectorization was explicitly disabled. Comparing the execution time of vectorization enabled and disabled, we defined vector efficiency. Vector efficiency is defined as the obtained speedup when vectorization is enabled compared to the vectorization disabled. To test our binaries, we have used a newly developed Fujitsu A64FX processor. This is the first processor that implements scalable vector extension. Each core is equipped with two SVE engines with SVE width of 512 bits. All our experiments were performed on a single core with no parallelization. On Table 2, you can see some of the selected A64FX hardware parameters. In Table 3, you can see the results for ETSVC benchmark. In the second column, we show the total number of vectorized loops for each respected compiler. we observe that ARM compiler for Linux was able to vectorize 100 loops, GCC 87 and Clang 67. In the right 4 columns, we report number of loops which yield a vector efficiency of more than 1.15, 1.5, 2 and 4 respectively. We see that despite ARM compiler vectorizing 13 more loops than GCC, some of these loops do not necessarily yield a much better performance than those for which vectorization was disabled. Number of loops which do yield a better performance is very similar between GCC and ARM compiler. Clang is lagging behind a bit, with number of vectorized loops around 20 less than the other two. Among loops that were not vectorized by any compiler, we tried vectorizing using intrinsic function. We were able to do so for 25 additional loops. Next, I would like to show 3 examples of such loops, where compilers failed to vectorize, but we were able to do so with not much additional effort. First example is a nested loop from function S126. On the left side, we see the loop written in C. This loop represents a case where induction variable, in this case k, is incremented both inside and outside of the inner loop in line 6 and 8. Furthermore, there is also a recurrence relation in 2D array bb over j. All 3 compilers failed to vectorize this loop. Reported reason was induction variable change outside of loop and possible recurrence relation. On the right side, you can see how this loop can be vectorized using intrinsic functions. In this particular case, we exchange the order of loops and use SVE gather load. This way, we can perform vectorization on elements which are not on contiguous locations in memory. The optimized version of loop performed up to 8 times faster than code generated by compiler. Second example I want to show is loop S212. This loop considers a case where vectorizing statements in the same order as written in C would lead to an error. If we take a look at line 3, we are accessing array element that is to be updated in the next iteration of the loop in line 2. All compilers fail to vectorize this code, with the reported reason of unsafe dependence of elements in a loop. However, this loop is easy to vectorize if we exchange the order of statements from line 2 and 3. On the right side, you can see the code with intrinsic. Notice that we first store the elements of array B in line 8, followed by storing the elements of array A in line 13. This is the opposite order as in the code on the left side. As in the previous case, optimized version of this code performed much faster than one generated by compiler. Last example comes from loop S241. This loop shows the case of node splitting, where both already updated element AI and not yet updated element AI plus 1 are needed in line 3. Compilers do not perform optimization due to reported backward loop carry dependencies. Solution to overcome this is to preload elements of array into vector register before performing any computation, which you can observe on the right side. These 3 examples should show that despite modern compilers being very good at vectorization, certain loops could still not be vectorized, and a manual vectorization is necessary. Next, we look at the results for Polybench C benchmark suite. In table 4, we show number of fully and partially vectorized kernels. In the middle column, we see the results for default configuration, and in the right column, results where arrays are called using the keyword restrict. We see that similarly to TSVC, ARM compiler performs most vectorization optimizations, followed by GCC and Clang. For GCC and ARM compiler, using keyword restrict increases the number of vectorized kernels. In figure 2, we see normalized execution time of different kernels for 3 selected compilers. We see that despite ARM compiler able to vectorize most loops, this does not necessarily induce the best performance. This might indicate that the cost models for successful vectorization are still not yet fully optimized for SVE architecture. Taking an average over all kernels, we see that GCC produces around 10% faster code than Clang and around 5% faster code than ARM compiler for Linux. In summary, ARM compiler for Linux and GCC perform better than Clang when vectorizing the code for SVE. However, it should be noted that not all vectorized code is necessarily faster. So when performance is critical, loops should be manually inspected in order to ensure the best optimizations. Using keyword restrict can greatly improve the compiler auto-vectorization. In the end, I would like to thank Huawei and Fujitsu for facilitating access to ARM machines.